So here we're going to talk about transformer TTRs, and one of the most important things I try to remind people is that when you're doing the transformer TTR, if you can do it single phase, you know what you're doing. It doesn't matter if you have a three phase, whatever, 20 degrees clock shift, the single phase TTR always works every time. So that I recommend doing that, but you have to understand that we're talking about the coupling of one coil to another. Now, I don't want to talk phase to phase. I don't want to talk how many windings. I'm just saying one coil to another. So let's take one of these data plates that we've been looking at, and let's see how we can break that down. Now, looking at this vector group right here, we already went over it in the last video. This is going to be a actually this is, I'm sorry, excuse me, this is a Y N 0 vector group. So if you have a three-phase TTR, make sure that you type that in there right, because if you don't, it's not going to spit out anything right for you. Now, what I quite often find is people don't know when and when not to use this square root of 3, right? So the best thing I like to do is just look at them from coil to coil. This is 3 single-phase transformers. And if you don't believe me, go ahead and look at the diagram right here, okay? There's one transformer, another transformer, and another transformer, okay? So if you look close enough, what you'll see is that this coil right here is my secondary, and I'm just going to redraw this over here, okay? This is my secondary, and it says X1 on the right-hand side and XO on the left-hand side, and if you trace it, what you'll see that the primary goes up to H1, and then it's tapped commonly across all the coils. I'll delete my little drawing here, and you can see that it's a common neutral across all of them. So this is my HO. Oh, look at that. That's just a single phase transformer. It's the same for all of these. Now, people get it confused between how many phases versus how many windings, right? This is a three-phase transformer. You have H1, 2, and 3. How many windings is this? This is a 2-winding transformer. I have a Y and a Y, okay? Now, what I like to say is how many coils are in this transformer? There's 6. So you can see 1, 2, 3, 4, 5, 6. If you multiply the number of phases, okay, and I'm going to do it like that, times the number of windings, that will equal the number of coils, okay? So if you remember that, you can always look at this and figure it out. Another cool trick that you can do, don't look at this neutral. That'll get you wrong every time. But look, you have 1, 2, 3, 4, 5, 6 right here. And this vector diagram is a direct representation of how it's supposed to, in a way, superimpose from one vector or one winding to the other. So given that knowledge, right, this is a Y to a Y. If you just remember that we're going to have neutral voltages on both of these, then what we're talking about is a phase to ground voltage from here to here, right? And so that means that both of these get a phase to ground voltage. So in order to do this, you could just use your phase, your neutral, phase to ground voltage and your phase to ground voltage, right? And that would be 7620 divided by 120 volts. So your TTR, if you tell it that you have a vector group of YN0, it should spit out a perfect ratio of 63.5. Now, what I would never want to see anyone do is say, oh, I'm going to use my phase voltage, divide that by the square root of 3, use this, divided by the square root of 3. Well, what do? You're doing 13,200 divided by 208, which, by the way, it's going to be the same number right here. And then you're also doing 1.73 and 1.73. The more you do with this, the more chance for error you introduce into it, okay? So don't use the square root of 3, like type it out 1.73, like use the full square root of 3, okay? And that is a very long number, 1.732, blah, 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 because if you don't use the exact number, you're looking for a 0.5% deviation on this for it to be wrong, okay? And a 0.5% can easily happen by not including the 3. You can get a 0.1% off by not including the 2. So make sure that you get the full square root of 3 if you really absolutely need it. Personally, I would just use the numbers that are on the data plate. Okay, if they're on the data plate, use the numbers. So we're talking about phase to phase voltages, or sorry, phase to ground and phase to ground, so you can use that. The next one, let's go ahead and take a look at this. This is it says it right here. We did it on the last one, a DYN1 vector group, okay? So you type that into your three-phase TTR, and it'll go ahead and it'll do the right calculation as long as you hook up H1 or H2, H3, and H1 all correctly, and then they're in the right order. So how can we calculate this one's TTR? Well, it gives us a voltage right here. That's our tap voltage. So make sure that you know what tap you're on. But this is the nominal. Nominal's typically going to be the middle tap, okay? Typically, not always, but most of the time it's going to be the middle tap. So this is a 69 kV on the delta, okay? And this on the secondary is a Y, and the Y voltage is going to be 4160 volts Y to ground, and it says, look at that, it says 2402. They didn't round it. They didn't just do 2400, right? So 2400. Now, for 2402. There we go. So this is where I want to really harp what we were talking about before. If you, I kind of cropped this picture to make it easier to see, but I'm going to go to this next slide right here. If you look, this delta, the way that these are done is you've got H1 right here and H2 right here, okay? Where does that induce on? Okay, that goes onto which coil? I'm sorry, in H3 right here. Well, let's look at the A phase coil. How can you find the A phase? Let's go, we have a Y on the secondary, so there's neutral and there's X1, so that means that this is our A phase coil, okay? That's our secondary A phase. Where's our primary? It has to be right across from it. This is my A phase primary coil. Okay, now we're getting somewhere. So where is this connected? Well, this got a wire that goes all the way over to here, and it goes to H3. So when you see sometimes the A phase in the primary is H1 to H3. This is why they're written like that. Okay, but I can tell you that if you go ahead and you do your numbers, what's your ratio going to be, right? Well, this coil, this is why I said use your coil values. Your coil right here is going to get phase to phase voltages, okay? And so that means that the primary is phase to phase. Primary, phase to phase. The secondary, though, is going to be phase to ground voltages. Phase to ground. Now, that's important, okay? Because that's how you calculate your TTR, and that's how your TTR is going to spit out your numbers. The only other thing it needs to know is your vector group, okay? And this one right here is just like the last one. This is a DYN1, okay? So let's go back to this last one because I don't want to use this one. It's got poor voltage configuration. So when we're looking at that, we said the primary, we know it's a delta, all right? It doesn't show the wiring diagram. I wanted to use that as a reference. So the primary is a delta right here, and the secondary, right? Another way to look at this, is H1 to H3, that's the leg that's directly parallel with this leg. Okay, so that tells you H1 to H3 is the same coil as X1 to XO. That's how these are drawn. This H1 to H2 is the same coil that, it induces onto the same coil of X2 to XO, all right? And the same thing for this one right here. And just if it makes you feel better, I'll go back to this other one. You can see that right here. Okay, so this is X1 to XO, H1 to H3. That's exactly what we did right here. And then I'm going to erase this. H1 to H2, XO to X2. Well, XO to X2, this is my X2. This is it right here. So the primary, we're saying that this is H1 to H2. Is that right? Well, this coil goes out on H1 and this connects over to H2. So yes. And the last one, I don't have to do it 3 times. You already know the last one has to be the last 2 remaining ones. So that's another way of looking at these which coil induces on which, okay? Now, given that, we know that the primary is a 69 kV. The secondary is going to have a coil voltage of 2402, right? So that's what you need to divide out. Don't use square root of 3 with this, but you can, okay? You could, but the problem is you might not get exactly 2402, but you always reference the nameplate. So if you do 69,000 divided by 2402, you get 28.72606. That's your ratio. Okay, that's what you should be getting. All right, so this is why using the full nameplate number is important, because if you're looking for 0.5%, that's tiny, right? So make sure you get the full number. Don't use the square root of 3, okay? Don't use a rounded square root of 3 is my point. Use the full square root of 3.